What's up?
Good morning, Professor.
Good morning, eBay.
Good. How are you today?
I'm good. How are you?
Good. Good.
Good. I got hi Gavin. I got a
Hello.
guy I got a guy coming in to work on some of our equipment, so I'll probably be a few minutes late. So just relax and pass that along to people as they log in. Class will start a few minutes late today. Okie dokie.
Yep.
Good.
I'll be back.
All right.
morning. Let me see all of your lovely faces.
Morning.
Morning.
Uh-oh, he's taking attendance. Uh-oh. What the? What the? Oh, in the wrong class. What the? Sorry about the late start here. We got a guy coming in to work on some of our trainers that are not cooperating. So, bear with me. I'm still catching up here. How'd the homework go? Anybody have any questions on the homework? Going once, going twice.
Oh, I did not do the homework.
Uh-oh.
So do I just go into class and do it at the end of the day?
Yeah.
Because I just got my book today.
Oh, you did?
Yes.
Just a second. I can't multitask for you know what. Is that everybody? Oh yeah. Oh yeah. Oh yeah. What are we doing? Oh, homework. Yeah, let's I was thinking about our schedule this morning. And anybody else still working on getting their homework, their textbook? Does everybody have their textbook now? Hey, if you're there, can I see your faces so I at least know that like I'm asking questions to people? You don't have to just put a hat on. Will your hair will, there we go. Your hair looks amazing. Except you're muted. Anybody else? Can I see anybody else? Where?
I'm good
The
now.
house. Carter just woke up. Gavin's still getting
Put a
out.
shirt on.
Hey, I'm here. I'm taking care of my brother. He's extra upset today.
Yeah.
Is it okay if I just watch the video?
Yeah, that's fine. Yeah.
All right. Thanks.
Okay.
Yeah.
So here's what I'll do. I'm just gonna start putting everything down yonder. And chapter 1, I moved it. So now you have an extra couple days to finish it. What I was thinking about this morning is maybe doing Mondays only Zoom Um, so if we do Mondays only Zoom, Wednesdays we'll come in and do a little bit of lecture and then labs, and then Fridays will be just lab days. So here's what I'm thinking. If I make the homework assignments due on Mondays, take quizzes on Wednesdays when you come in, do the lab work as we go, and then Fridays will just be open lab days. So basically what I'm saying is I'm not going to take attendance. It's up to you guys to be here for the lectures, watch the lectures online or whatever you need to do. And then you have so much lab time during the semester to get your labs done. Am I making sense or no? You guys like, what the hell are you talking about, Zach? Like, what the hell are you talking about?
So is this going to start next week?
It's like talking to a bunch of mimes. Okay, yeah, that's what we're going to start next week. Okay, so if you got chapter 1 done, you're golden. You can work ahead on the other chapters all you want. So chapter 1 will be due on the 29th. We'll take a quiz on chapter 1 on the 31st. And then Fridays will be open lab day. And attendance is going to be optional throughout. I'm still going to take attendance. So that way, if you come to me like the last week of the semester and say, hey, bruh, I don't have all my stuff done. What am I going to do? I'm going to say, well, you didn't show up the month of April. You know what I'm saying? Feel me? Yeah? No?
I got you.
Thank you. Okay, so that'll be the tentative schedule then. So this coming Friday, 2 days from now, come into the lab if you so choose, and we'll get started on lab work. Today, I guess we don't need to worry about the homework. We don't need to worry about a quiz. So I'm just going to get right into the motor theory, and hopefully we'll start looking at some ladder diagrams. Okay.
On the 2nd there, on April 2nd, will there be class in the morning? Is that what that's saying?
Yeah, we have the college is open on, what is that, Good Friday?
Yeah.
So yes, but that will be a lab day. So if you want to sleep in or go to church or whatever you want to do on that Friday, you can do that. Are you picking up what I'm throwing down about Fridays being open lab day? So just plan on every Friday from here on out. I'll be here from 9 to noon or whatever. If you want to come in and work, you can. If you want to come in and work on something else, you can. It's your time. Okay? So Mondays will be Zoom only. Wednesdays will be come in for class. I'll still record the thing if you can't make it in that morning. And then after the lecture, the first part of class on Wednesdays, then we'll do lab work. You got to cut you loose to go in the lab and work on what you need to. And then Fridays will be all lab. There'll be no homework due, no quizzes on Fridays. That's going to be the tentative plan. The funny thing is I have it all worked out here in my big dome, but then like in 2 weeks, it's all going to change anyway. So you guys are a tough crowd. You know that? I swear I'm talking to a bunch of mimes. Do me a favor. Somebody go like this. There we go. Now at least I know what I'm dealing with. Okay, I'll stop screwing around. Anybody know how motors work?
No.
A little bit.
A little bit, rough idea. I'm going to give you my little spiel here. And unless I'm actually talking about the homework, the textbook itself. What I give you in class is for you to take and use in the lab. You know what I mean? So you're going to have your book work for this class, and you're going to have your ZAC work for this class. So we need to know how motors work, because remember, all we're going to do when we go into the lab is we're going to turn motors on and off, right? Pretty simple. But let's figure out how they work first. Anytime, oh, look, there's two of me. That's sexy. I like that. How do I change
I
that?
learn twice as much now.
That's better. What'd you say? Somebody make fun of me? Don't you ever talk
said
about me that way?
We're gonna learn 2 times as much now.
That's right. Okay, what are we doing? This. What just happened? That's not good. So. Whoop, whoop. Yeah. Okay.
Can I use this?
I don't care.
Can I snip this?
Probably not. Unless Steve says it's okay.
Okay.
I don't know where you got it or what it's for.
I
or
got it in
anything.
this room. I don't know what it's for. It's in a box.
Oh. Ask Steve. If it was me, I'd say, yeah, just cut the hell out of it. I don't care. Okay. Right? And I put current through it. Anything happen? Any ideas? Will?
Sound was
Yes,
sound
that's
was
right.
cutting out.
Yes. Yes. When you put current through a wire, you're creating a magnetic field. Anytime you have current, you have magnetism. Okay? So how can we use that? If we can control it somehow, we can make a shaft spin, right? Basically, what this all breaks down to is if I have and this would work a lot better with solid wire. I create a loop with this thing. And I'm going to kind of square it off because the edges of it need to be at a right angle with the magnetic field. What I'm going to do is make the current interact with some magnets that I place around this thing. Okay, so here I have a loop and I kind of squared it off. There's something called the right-hand rule of magnetism, where if you were to take your right hand and wrap it around this thing with, Will, do you have a question?
No, I thought, never mind.
Oh, okay. And you put your thumb in the direction of current flow, the way that your fingers are wrapped around the wire is the direction of magnetic field that you create. Okay. So if you can imagine in this little coil that I put here, and this is scaled way down, and unless I had a huge amount of current flowing through this wire, I don't think I could get this to work, but this is just an example. Okay, so if I introduce two magnets to this thing, what the? North pole, South pole. I put current through here and I got a plus and a minus. The sides of this coil that are right angles to where this magnetic field is, they're going to create a force in the opposite direction of each other, right? Because of that right-hand rule of motion, current's going this way. If this is plus and this is minus, current's going this way, so magnetic field wraps here around this way. And on this side, right-hand rule of motion, current's going that way. And you end up with a force downward on this side and upward on this side. Does that make sense? It's a phenomena. I can't show it to you unless I actually hook this up. But this little bitty wire couldn't take that much current. But this is just the theory behind what makes a motor spin. Okay? So if I have plus DC current here, and this is minus, and I start to get an upward force here, right? If I spin this thing all the way up, so I apply current to it, it's going to end up coming up like this. So this is at a 90-degree angle to where I started. At this point, everything stabilizes and stops, okay? Because the magnetic fields have aligned. So what DC motors do is as soon as they start to approach this point, the polarity changes, and it changes from this was plus and this was minus. It flips now, okay? This becomes minus and this becomes plus. And what that does is as it reaches this point, this magnet starts pulling this side to it. Make sense? Okay, so then we get this way and we go down and it equalizes again and the polarity changes again, and then it keeps going like that. So the thing that changes the polarity in a DC motor is called a commutator. That's the sole purpose of the commutator, is it reverses current flow in the armature as the motor spins. So that's a DC motor. I have a DC motor here. I was trying to take it apart so I could show you the guts of it. DC motors are really easy to control the speed with, because as you raise the voltage, you raise current through the windings, creating a stronger magnetic field, which makes it spin faster. Lower the voltage and it slows down. But DC motors are pretty expensive to make. DC current, high voltage DC current is hard to come by unless you have a big converter. And it's hard to control torque with these things. So that's why, for the most part, in commercial industrial applications, you're going to have AC motors, which we're going to talk about next. I'm trying to see if I can get this thing out of here so I can show you the frickin' commutator. You little jerk. The windings are in the way. Oh, I got it. Cool. Okay, so anyway, you look inside here. If you ever have trouble seeing on these cameras, I'm kind of experimenting with these different cameras here, but you can see how there's two sets of windings in here, creating basically a magnetic field, a magnetic north and south pole. And then on the armature, the rotor, These little guys here are actually what reverses the current flow. It's kind of cool. I don't really take DC motors apart very often because I don't hardly ever use them. Anyway, that's a DC motor and basic motor theory, basic motor principle. AC motors, alternating current. Have y'all taken 133 yet?
Absolutely.
I think eBay, you're taking 133 this semester, right?
Yes, Professor. That's right.
Okay. So you're going to get some AC sine wave stuff if you haven't completed AC theory yet. Anyway, just bear with me. We'll get it taken care of. This is the inside of an AC motor. Okay. Before it's taken apart, it looks like this. Big old mumble jumble. This is a Baldor industrial 3-phase motor. Anybody know what this part of it is called?
The nameplate.
Nameplate, awesome. And what kind of information do we have on there?
Like what voltage it runs on, how many amps it is, like the horsepower and all that.
Yep. They're required to put all this information on here. The manufacturer is, and it has category number, specification, frame, serial number, horsepower. This is a third 0.33 or a third horsepower. This motor will run 208 volt or it will run 240 or 480. It shows you your current, RPM. We know what RPM stands for, revolutions per minute, right? So if you put 60 hertz alternating current on it, it will rotate at 1,725 times per minute. Pretty fast, right? 60 hertz, blah, 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 blah. The most important things that you're probably ever going to use are the horsepower, volts, and current. And then we have two different options to connect all this mess, which we will talk about later. This is a 9-lead 3-phase motor. Anyway, that's what a motor looks like before you take it all apart. And then what's this part called?
It's like the junction box where you make up all your connections.
That's what it's, but there's a name for it.
Huh.
Get ready to giggle. This is called a peckerhead.
Ah.
No joke. That's what it's called. Peckerhead. I always get some gigglers anyway. I think I'm immature, so I'll probably laugh every time I say it, but it's a peckerhead. Anyway, you're right, though. That is the junction box where the connection is made. All these wires sticking out are the ends of these windings. So this has, I don't know how many, it looks like this one's been burned up, which is maybe why it was taken apart. But we go 1, 2, 3, 4, 5, 6, 7, 8 sets of windings. What do you think those windings do? They create magnetic field, right? Same as a DC motor. So we put current on these windings, it's going to create a magnetic field. But why do you think, in the DC motor, we had a north and a south pole, and they were just opposite of each other, right? And that thing spins like that, with the polarity changing every time it spins. Okay. Why do you think we have so many windings here and they're kind of all in a circle?
The current alternating polarity already, it just needs those stations to keep it rotating.
Exactly. Alternating current changes polarity already by itself. It's doing the work for us. All we have to do is harness it and try to control it. I'm going to pull up a little thing here. So if we break this thing down to one sine wave, okay, so here's our alternating current sine wave. And this is in 1/60th of a second. So from this spot here to this spot here is 1/60th of a second. And let's simplify it even further and say that there's only 2 sets of windings. Okay, and I'm just going to redraw them over here. Got a set of winding there. And a set of windings here. Okay, and then we've got the rotor on this thing, which I'll show you really quick. It's kind of cool. This is what the rotor looks like. Why do you think this is called the rotor?
It rotates.
It rotates. Very awesome. There's a little bearing on here, right, that the end sits on. It's got a fan on there to cool itself off as it spins. And here's some internal windings. Okay. It's got bearings on both ends. But this part actually rotates inside of here. This is called a stator. Why would they call it a stator?
Stationary.
Stationary. So you got a stationary stator and you got a rotating rotor. Makes sense, right? Okay, so let's magnetize little thing here. Oh, that looks like crap. Ah! North, south. Okay, and you got 2 sets of windings. So the windings represent these guys. So I'm just breaking it down to like 1 set. Okay, so in reality, there's a burnt up set inside here, and then you can see these sets on the outside. Okay, but I've just broken it down to 1 magnet and 1 set of windings. So as this current approaches its peak, what happens is you're creating a magnetic field in these windings, correct? And as the current gets higher and higher and higher, that magnetic field gets stronger and stronger. So as I'm approaching this peak, let's just say this north pole is approaching this winding, and the south pole is approaching this winding. Okay? And that pole gets stronger and stronger and stronger until it gets past its peak. And then when we get down to this point, from 133, those of you who have taken it, what is this point called? Called the alternation, right? We're alternating current. So basically in an alternating current circuit, the current is going back and forth 60 times a second, right? DC circuit, little light bulb here. Current is going to flow in one direction all the time. In an AC circuit, my drawing is amazing, isn't it? In an AC circuit, current is changing directions 60 times a second. It's going this way, and then it's going that way. It's going this way, and it's going that way. Back and forth, 60 times a second, like that, okay? During this point in time, when the current changes direction, polarity changes, now we're starting to feel a pull of this magnet is going to start to be pulled by this winding, right? And then this magnet is going to start to feel pulled by this winding. Make sense? So what you're doing with an AC motor is in this stator, you're creating a rotating magnetic field that the rotor is following. Make sense? Okay. Now we're going to get into three-phase motors, three-phase AC. Okay, so that last example I gave you, you had one single phase of current. Now we've got three. I guess my colors are down here. So I'm going to go black. Then I'm going to go red. And I'm going to go blue. So I got three different sine waves. Right? Make sense? So 60 times a second, this voltage and this current is going black, red, blue, black, red, blue, black, red, blue, black, red, blue. But they all change direction the same way. The only difference with this, and this is a three-phase motor, is you have three different sets that you're working with, right? So it's the same example that I gave last time. You've got a blue north and a south. Oh, this is gray. These are windings. Red north and the south. And a black north and the south. Okay, and then you've got, what's up? What's up? You know our former dean of this department, big deal, right? Just walked in here and flipped me off. Can you believe that? Just no respect for life.
Not very Dean-like of him.
Not very dean-like of him.
Vicious rumors. It's all a lie.
Yeah.
Do not believe what he says.
Get out of here.
That wasn't my finger.
Yes, it was. It's going on YouTube, by the way. Is he? Okay. What were we doing? Oh, three-phase. Same deal. Okay, so let's look at the black phase. If this thing is, I'm just going to say plus and minus to make it not very confusing, but this thing is being drawn to the north and south pole of the black as it's starting to be, I guess it would be going this way. Since we're going, which brings me to another point. If I'm starting with the black, I'm going to start with this guy right here. Okay, and this is rotating our shaft. As we're approaching our peak of the black phase, it's starting to pull north to south this way because the current is creating that magnetic field, right? Then, as we approach the peak of the black and we start to go down, screwed up again. Since we're going black, red, so the reason I'm screwing up is because the phase sequence is black, red, blue, right? So if it's going black, red, blue, it's got to be going in this counterclockwise direction, right? Make sense? Okay, so back step a tad. Approaching the peak of the black, we're getting pulled in this direction. Once we reach the peak and we start to go downhill, now we're about here, and we're starting to be pulled towards the red set, right? Then as that one alternates, we're approaching the blue peak, right? And then we're going to be pulled towards the blue set. I know my drawing sucks, but this is making sense, right?
Yeah.
Okay. The other thing that happens here is it's kind of a push-pull, right? So as our let's say our red phase alternates at this point right here, it's now going to be pushing that shaft away from it as it's being pulled back towards the blue and the black. Does that make sense? So each phase is doing a push-pull simultaneously, kind of in sequence. 10-4? That is the basics of motor theory. So you got DC motors, you got AC motors. And then within each category of AC and DC, you've got different types. It all just depends on the application that you're using these motors for. But I don't really care to get into all the synchronous and squirrel cage and all that different stuff. It's just important to understand the principles. Follow? Any questions on motor theory?
I don't have any questions about the motor theory, but I have a question about, are you recording on that little picture you have of the motor? Because it says 0 out of 23 minutes with the little red dot. Did I make any sense or no?
I am making sense. No, I am not recording on these. I'm recording on Zoom. So Zoom is recording this entire screen share.
Okay, I just didn't want you not to have one part.
Yeah, and I really appreciate you looking out for me. I'm just using these web apps to have two cameras on the screen at the same time so I can show you different, because eventually I'm going to have components over here and I'm going to have a ladder diagram right here. You know what I mean?
Okay, thank you.
Appreciate that. All right, let's take a little break, and when we come back, we'll start looking at some components. Say meet you back here about 5 after.
Thank you.
Good.
No, thank you. You guys want me to pause the recording so you can talk bad about me behind my back?
I'll do that anyway. Like, I'll do that on the recording.
Okay, go ahead, M Daddy, whenever you're ready. Okay, I'm back. How was your break? Everybody good?
Yep.
Everybody get arrested?
During that 10 minutes.
Ethan got arrested? All right. Yeah. It's a challenge.
I need more time.
Anybody can get arrested in 10 minutes, but can you get back in time for the next part of class after you get arrested? That's the hard part. Ugh. Okay. Everybody know what this is called? Shh, don't look, don't read it. What?
The contactor, motor starter.
You could call it a contactor. Yeah, it's a relay. This is not a motor starter. I'll get to a motor starter in a minute, but I wanted to show you this first because it's kind of like a motor starter, but simpler.
Yeah.
So what does this thing do? What's the point of using a relay on anything?
It's a simple way to, or a more difficult way to turn it on and off.
Yeah. It's used to turn things on and off. As much as you guys want to see my face. This is the symbol for relay contact. It's normally open and that's normally closed. Okay, so just to show you what happens is I'll just make this L1 in neutral. Put some lights on here. So these are relay contacts, normally open, normally closed, and these are lights. Let's say that they're yellow lights, okay? So just how this thing sits right now, are either of these lights on?
The bottom, the normally closed one would be on.
The bottom one is because this is closed. A current can flow through here, right? So this is on, all right? Let's call this CR1. This is also CR1. So on this drawing, we're pretending that this is CR1, okay? How do I turn this one on?
If it closed the relay.
Yeah, but I can change it, right? So on a relay, you have a set of contacts. Always, always, always you have a set of contacts. On this one, you have 4, and they are right here, 2, 3, 4. And if I could zoom in with this camera, I'd show you. I don't know if I can, but this one right here up at the top, this is an Allen Bradley relay, and they all have these. It's just you got to look really close. This is normally open. This is normally closed, open, and open. Now, one way you can tell sort of easily is you see how these rivets down here look differently on this one than they do the other 3. That's because this one is normally closed. They're normally open. And I'm going to take this thing apart in a minute and show you how it works. But to change the state of those contacts, you have to energize a coil. There is a coil in here, and actually you can see part of it right here. This is a 24-volt DC coil. The contacts for the coil are here and here, okay? So inside of here, there's a wire that just goes round and 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 round. Goes in and then comes back out. That's it. That's all a coil is. It's just a coil of wire, okay? When I put alternating current through this thing, what happens? We were just talking about magnetism. When you put alternating current through this coil, what happens is it creates a magnetic field and pulls the contacts in. And I can show you that with this little red indicator. If I energize this coil, let's say now, this thing will pull in. You'll see that depress. It creates a magnetic field that pulls that thing in. Right now it's being held out with a spring. Okay. Energize the coil and it goes like that. When that happens, all the contacts change state. So where this, and this were open, now they're closed. Where this one was closed, when I do that, now it's open, okay? And I'll demonstrate that with my meter. All right, so this is you see when I have continuity, so current can flow, I get a beep. Can you guys hear it?
Yeah.
Okay, all right. So this is a normally open contact. I'll put my leads there and there, if I can hold them there. Not there, not there. Okay, now I'm gonna push this coil in. So I'm pretending that I energize the coil with 24 volts. I push it in and it makes those contacts. So this, what I'm doing right now, represents on your screen go. This is a normally open one, but if I energize the coil for CR1, it will close this and turn that light on, okay? If I energize the coil for CR1, it will open this one and turn this light off all at the same time, okay? There's only one coil on here. If I energize that coil, it changes the state of everything, okay? And then just to show you this normally closed one, I should have continuity here, and I do. Push the coil in and what the there we go. What's going on with it? There we go. All right. I got some dirty contacts or a bad coil or something, but you get the idea. Let me take this thing apart to show you how it works. This is a type of component called NEMA, National Electrical Manufacturers Association. It's a style of components that's usually big, bulky, robust, can handle a lot of wear and tear. The other cool thing that I like about them is that you can take it apart and replace things on it. So if this contact actually did go bad, like I was just showing you, I could take that contact out and replace it. Anyway, I just want to show you the guts of this thing so you can see how a relay works. This little bad boy off. And you can see that this red indicator is being held in there with a spring. Okay. I already showed you the normally open, normally closed tabs. I know it's hard to see on the camera, but you'll see it when you get in here. So this is a normally open contact that I'm going to take out now. I need a smaller screwdriver. All right, so here's the cool part. Ready? Let's say, well, I don't need all these normally opens. I need 2 normally closed and 2 normally open. Well, I can take this thing out, flip it around, and it becomes normally closed. Isn't that so cool? I mean, you see on this side of that little tab, it's got the normally closed symbol on. You're not gonna be able to see it. You'll see it when you get in here. And you're welcome to, if you want one of these when you get in here to take it apart and see how it works, you're welcome to do that. But basically what it all comes down to is the way these little tabs here are oriented. Okay, so in the normally closed direction, remember it's being held out like this by that spring. And then when the coil energizes, it pulls that in. And watch what happens. The contacts are inside of here, if you can see that. But when this drops down, it breaks contact. If it was in this direction, it was being held like this. When this is normally open, remember, so right now it's apart. These 2 points are apart. But if the coil pulls in and this comes down, then it makes, right? So normally open, coil pulls in, and it makes between these 2 points. So that is your contact. I could make this one normally open too if I just took these screws out and flipped it around. Cool. I don't know that I'm going to be able to without turning this around. Put these guys back in so I can take the other screws out and show you the coil. Get in there. Take these 4 outer screws out. Here is your coil. Oh. You can see that there's going to be a spring in there that pushes this thing out, right? There's your spring. And your coil is, I'm not going to take that all the way apart. The coil is in a figure 8 on this thing. So if you can imagine the coil, wires going in, wire coming out, and it's going wrapped around in a figure 8 fashion. Okay. So when that thing gets energized, it creates a magnetic field that pulls this thing in. Right now, this is being held there, held out by a spring. If that spring wasn't in there, it would just sit down in there, right? But if I energize the coil, that thing at the bottom, this guy, oh, this is the other part of the magnet. I'm sorry. I just pointed at the other side. Okay. That coil is going to create a magnetic field and pull this thing in, changing the state of the contacts. Make sense? So that's how a relay works. You're always going to have a coil, and you're always going to have some contacts that are changing state. Back together later. So in our little diagram over here, there's something missing, right? What's missing on this diagram that's going to change the state of the contacts?
Coils.
The coil, right? We're showing the contacts of that relay, but we're not showing the coil. So this is what the symbol for a coil looks like this. That's it. That's the symbol for a coil. So we'll label this CR1. And on this diagram, we have 3 components of that control relay 1. We got 2 sets of contacts, and we have the coil. If I energize this thing right now, this would just change the state of the contacts. But what you have in most ladder diagrams are some kind of input that's gonna energize the coil. And I'm getting kind of above and beyond where I'm trying to take you right now. But just for an example, this is the symbol for a push button. I haven't even talked about push buttons yet, but we will. If I push this push button down, it will close this contact or close this set of points, energizing this coil, which changes the state of these. So this becomes closed, this becomes open, and this turns off, and this turns on. Make sense? If I let go of that button, this opens back up, de-energizes the coil, and changes the state of the contacts back to how they were. Turning this one on, turning this one off, closing that, and this is back open. Got it? Questions on relays?
Yes, that relay you showed us, it had what, four different terminals on it. Are you able to do like a circuit on each one?
What was the last part?
Are you able to do a separate circuit on each terminal?
Yep. So you can control 4 different outputs with this one relay. So that's one advantage of using a relay, right? If I push a button and I want 4 different things to happen, turn on or off, you would use a relay for it. The other reason we use relays is because, let's say I've got a 480 volt I don't know, fan. I got a 480 volt single phase fan that runs at like 20 some odd amps. Would a regular little toggle switch, a light switch, work for that? No, because those are usually rated for like, I don't know, 10 or 15 amps. With these guys, you can use a very small voltage to control big loads, right? This one itself was a 24 volt coil. And these contacts, I'm assuming, are rated probably 30 amp. Doesn't say on the contacts themselves, but this is saying half an amp and 1 amp. That's not right. These contacts can take more than that. Okay, here's a 120 volt coil. This is the kind you will see on your trainers in the lab. Okay, so we're going to energize 120 volts on the coil. Works the exact same way. This one happens to be normally closed, open, open, open. So when I push this down or energize the coil, this one opens up, this one closes, and this one closes. Okay, these contacts are rated for 60 amps. That doesn't seem right either. Typically, what you see in contactors and relays or these contacts are somewhere around 30 amps. That's what they're rated for. Okay, but these will always have a voltage rating on the coil, and they'll always have a current rating on the contacts and a voltage rating, but current is what you're going off of. Okay, so I could put a 480 volt, 25 amp fan on this one contact, and I could control it with a 120 volt signal. Make sense? Okay, so that's relays. This is the exact same thing, except for one difference. I need my Kleenex box to raise this camera up. The only difference, this looks kind of crazy, right? The only difference between that and this, these little guys right here. And on this one, they're missing. They'd screw into these locations. But this is where overloads go in, a thermal overload. This guy. Okay, this is a thermal overload. These are rated for different amounts of current and heat, but I'm not really sure off the top of my head what W35 means. But every motor itself is going to be rated for a certain size overload. What this does is protect the motor windings from overheating. Okay, so we all saw those windings that were inside the motor earlier, right? This is what actually protects that thing from overheating. This is not an overcurrent device. It's a thermal overload. Okay, so when this thing is on here, this little spring, this little element right here will start to expand, turn this little gear, and open up the circuit. This is an Allen Bradley NEMA type motor starter. By the way, I don't know if I told you this, but this is a motor starter. This is a relay or a contactor. This is a motor starter. The only difference is the motor starters have overloads on them. Okay, these are nice because they have a little window here that tells you when the overloads have tripped. If a motor overheats and trips the overloads, you have to wait for the motor to cool off. Press the reset button and it will reset itself. The other nice thing about this is you see on this little off That's actually written on the coil part of this. I showed you the inside of this one. On the inside there, it says off. And when this coil, this is the coil here, changes state, it goes bloop. Now it says on, right? So if I put 120 volts on this coil, it will pull the contacts in the same way that this thing did. It'll go bloop and make the contacts. The contacts on here are these 3 points and these 3 points. So this is designed to turn on and off a 3-phase motor. Here's your lines coming in. All right, so we're going to supply in the lab. In your labs, we're working with 208 volts. Okay, so we're going to bring in 3-phase 208 to here. And then to turn the motor on, here's our 3 wires going to the motor. We're going to energize this coil. Okay, so input, output to the motor. And normally open is, I mean, where'd I go? This guy here. Okay, so right now the motor is off. These 3 fingers that I got going on here, these are going to the motor, right? I energize this coil, that closes and turns the motor on. The only difference between this and that is it has to run through these overloads. Make sense? So on your print, when you're wiring up your labs, here's what you're going to see. Where'd my frickin' mouse go? There it is. This is what you're going to see on your labs. This is the power circuit. Later on, we're going to talk about the control circuit. So just by looking at this, can you guess where the motor is?
It's the circle, the circle with M.
Yep, M1. This is right here. Ah! Ah! This is the motor. Okay, we got 208, 3-phase, 60 hertz coming into this system. This part right here, this is a disconnect. I don't have a disconnect with me, but you will see on your trainer what a disconnect is. You guys know what a disconnect is off the top of your?
Absolutely.
Okay, so you're gonna have some kind of, you're gonna have a gray box. Let's go grab one so you can see what it is. Be right back. What? There's a disconnect. Reverse osmosis. Anyway, what I wanted to show you is disconnects always got a lever like this on the side. This is what actually turns it on and off. It's really old and rusty, so it doesn't work very well. But inside of there, on yours, you're going to have 3 fuses. And all it is an in and an out. Okay, so this is how you turn the whole system on and off. Okay, when I turn this thing on, you'll see these 3 little knife blades stab into the back. Okay, so these just made back here. Now I have continuity from this end to this end through these fuses. So if something goes awry and gets grounded, overcurrent happens, these will blow. That's what a disconnect does. I take our little lever that's up here on the disconnect and I throw it on, it'll close these. So now I have 208 volts all the way across here through these fuses. But the motor's not going to turn on yet, right? Because somewhere down in the control circuit, which is going to be down here somewhere, which we're not even getting into this yet, I'm going to have some way, shape, or form to energize this coil. When that happens, these three contacts close. Boom, 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 turning the motor on. See what I did there? That is your basic power circuit. So when you see more complicated circuits, like for example, well, can you guys see yourselves? No.
No.
Hang on a second. I'm gonna grab a future lab ladder to show you guys. So here's the same thing, right? You should recognize all this stuff up here, right? We just went over that. Now this is the power circuit up here. This is the control circuit. We'll talk about all this later, but the gist of it is when I press this push button here, the motor starter coil, which is this, energizes, does this, and closes these contacts, turning the motor on. What sound does it make? Thank you. See what I'm saying? All right. Everybody good? Threw a lot of information at you today, but my hopes is that you guys come in on Friday. We'll go over a few more things and get you started on your labs if you'd like, if you can make it in on Friday. Do you have any questions about anything that I went over today?
No, sir.
Think you're good? All right. Well, I think I've given you enough to stew on today. So we've got, what did we decide? Monday is homework's due. That's Monday's going to be Zoom. Back up this coming Friday. Come in if you can. We'll talk a little bit more and you can get started on your labs after that if you'd like. If you can't come in Friday, just hop on Zoom. I'll record everything anyway, just in case you miss it. Monday we'll be back on Zoom. Talk a little bit more. That's when your homework's due. And then we'll do our new schedule that we talked about this morning. Wednesday will be lecture lab, and then Friday will be lab day. Cool.
Yes, sir.
Cool.
All right, fellas. Well, I will get this recording on YouTube and post it to the Google Drive as soon as it gets processed. And you have a lovely rest of your, what is today, Wednesday?
Yep.
All right.
I do have a question regarding the DC motors.
Yeah, what's up?
You mentioned the commutator reverses the current flow. Is that a separate unit, or is that just a different name for, instead of like the alternator motors had the rotor, is that just a different name for Stratter, or how does that work?
I'm not sure I understand your question, but it's part of the, it's built into the motor. Let me see if I can find a picture of it.
Okay.
Okay, so on this thing, well, this is a good gift. I need to save this. Okay, so you got your coils on your rotor. Here's our coils in here. This is the commutator. Brushes, the brushes that supply current flow to the coils hit this thing, right? And then as it hits another set, it reverses the polarity going in and out of those coils. Does that make sense? It's built in.
Okay. Yes. Okay. Thank you.
Any other questions?